All right, my friends, let's do this. Let's use the elbow method to find the optimal number of clusters. So we're going to use, of course, the WCSS, which is the within cluster sum of squares. I will remind what this is, but first, let's create a new code cell to start this new step of the implementation. All right, so what are we going to start with here? Well, we're going to find back our very good friend Scikit-learn, because we will actually implement that elbow method with a class of Scikit-learn, which, guess what, is called, well, k-means. Because indeed, the way we will implement the elbow method will actually be by running the k-means algorithm with several number of clusters. So you see, we're going to run the k-means algorithm several times, each time with a different number of clusters. And that's why we have to call that k-means class that can run this algorithm already. And so, well, our first step here will be to start from Scikit-learn, from which we're going to get access to the module that contains that k-means class, and that module is called cluster, just like that, and then from which we are going to import that k-means class. Perfect. And now, what do you think the next step is going to be? Well, exceptionally this time, the next step won't be to create an instance or, an object of this k-means class, because we're about to start a for loop which will run the k-means algorithm with 10 different numbers of clusters. So very simply, we will run the k-means algorithm with one cluster, then with 2 clusters, 3 clusters, etc. up to 10 clusters. And therefore, the way to do this is through a loop. And we will do a for loop because we know exactly the different numbers of clusters we want to try, which are from 1 to 10. And each time we run the k-means algorithm, with these different numbers of clusters, well, we will compute, of course, that famous metric in clustering, which is, as I told you at the beginning, WCSS, the within cluster sum of squares, which I remind is defined as the sum of the squared distances between each observation point of the cluster and its centroid, the centroid of the cluster. So we're going to compute that sum of these squared distances, and this is exactly what will be on the y-axis in the graph of the elbow method. Remember, the graph in the elbow method contains in the x-axis, well, the different numbers of clusters we will try from 1 to 10, and in the y-axis, it contains the WCSS computed for each of these numbers of clusters. And therefore, here, what we have to do right before starting this for loop is to create a list which will, through the for loop, be populated with the successive WCSS values, for each of the numbers of clusters. And therefore, we're going to call that list WCSS, which we will initialize as an empty list. Remember that lists in Python are written in a pair of square brackets. So here, in this pair of square brackets, we're going to add one by one the different WCSS values for each of the numbers of clusters. Okay, and now we can start the for loop. So the way to write a for loop in Python is to start with for, then we choose a name of the iterative variable, which will be incremented by 1 each time in each iteration of the loop. And the classic name for that variable is I. And then we add in range, and here we specify in parentheses, well, the values we want this index of the loop to take over the iterations. And here that's very simple. I will actually take the different values of the numbers of clusters we want to try, which are from 1 to 10 included. But remember, ranges in Python include the lower bound but exclude the upper bound. That's actually what we see here, start defaults to 0, okay, so that's the default lower bound, and stop is omitted, right? It is excluded. So that's why I also really like Google Colab. You have all the info in this little help window, but I'm also here for the explanation. So there you go. The range we have to input here is from 1, the first number of clusters we will try, and then up to not 10, but 11. Because we want to include 10, and therefore we have to go up to 11, which is excluded. All right? And then we add just a little colon, just like that, and then we start the for loop. All right, and now can come the next natural step, after we import this class, the k-means class, because indeed, now we can create our first k-means object. Why do I say our first k-means object? That's because once again, we're going to create 10 different k-means objects for each of these numbers of clusters from 1 to 10. So here we're creating the first k-means algorithm, which will be run with, therefore, one cluster, because I here starts at 1. All right, so let's create our first k-means object, which represents exactly the k-means algorithm, which will be run to identify, well, actually some one cluster. You see what I mean? And then I will be equal to 2. So that new k-means algorithm will be run to identify 2 clusters. And then a new k-means algorithm will be run to identify 3 clusters, etc. up to 10. Okay, there you go. That's our first object, which we create by calling, of course, the k-means class. Be careful with the capital letters. K-means class, we add some parentheses, and now we import the arguments. So the first parameters, obviously, is going to be, well, that number of clusters we want to identify. And that name of the parameter is n_clusters, which stands for exactly number of clusters. All right, and this should be equal to what? Well, if you understood the way this for loop works, of course, the number of clusters here is I, which starts at 1, then will be equal to 2, then 3, up to 10, which are the different numbers of clusters we want to experiment in order to plot that elbow method graph. All right, so numbers of clusters equal I, and then we would like to do something to avoid the random initialization trap, which was explained by Kirill in the intuition lectures. And the way to avoid it is to initialize the k-means algorithm with a particular method, and that method is called k-means++. So it's basically an advanced initialization trick, which will make sure we don't fall into the random initialization trap. So we must absolutely input that parameter, and the name of that parameter is init, and the value to select, well, that k-means++ initialization is called, in quotes, because that's a string, k-means++, just like that. All right, so now we're safe from the random initialization trap, and now we will just add one final argument. You know this one very well. It's just in order for us to have the exact same results on our notebook, so that we can, follow and describe what's happening on our notebook. And that parameter is, of course, random_state, which we will set equal to 42. 42 apparently is a number that brings luck in mathematics. I'm not saying that I believe in this, but anyway, we just have to fix the seed here, and any number is okay as long as we choose the same. All right, so 42. And now the next step, because we only created the object so far, we haven't run the algorithm yet. Well, here we go. That's the next step. The next step is to run the algorithm. And by running the algorithm, I actually mean train it. We're ready to train the k-means algorithm with that I number of clusters. And as any function, especially in the Scikit-learn library, but also, in a TensorFlow library, well, the function used to train an algorithm, a machine learning model, is the fit function. Here, a method, because it will be called from this k-means object. So there you go. The next step here is, of course, to take, well, our k-means object, from which we're going to call that fit method, which will take as input. Well, you're going to tell me, what does it take as input? It takes as input this time, of course, only the matrix of features X. Because remember, in the graph that was shown to you to explain the intuition lectures, well, in order to train the k-means algorithm, we only need the data of the features. And here, as a reminder, we are training the k-means algorithm with only the annual income and the spending score. And you will see that it will be way enough to identify some patterns, some clusters. All right, and that's it. That's only what we have to input to run or train the k-means algorithm. And so now, according to you, are we done with the iteration of the loop? Well, no, because remember, we're only doing this to get one particular thing, which we already initialized. I'm talking, of course, about the WCSS value, which is the within cluster sum of squares between the observation points in each cluster and the centroid of each cluster. So there you go. That's exactly what we have to compute right now that we already trained and run our k-means algorithm. And well, the way to get that WCSS value is to first take our WCSS list, which is so far initialized as an empty list. And then we're going to use the append function, which is a pre-built function of Python lists, and which will, of course, add or append, a new value inside this list. And the first value it will append, of course, is the WCSS value computed for one cluster, which is therefore actually the sum of the squared distances between all the observation points, because there is only one cluster, and the centroid of the single cluster. All right. So append, since it is a function, I'm adding some parentheses. And well, the way to get that WCSS value is to call an attribute of the k-means object. Objects in classes have attributes which can give you directly some values you want. And well, luckily for us, there is an attribute of the k-means class which is called inertia and which will give us exactly that WCSS value. All right. So in order to get that attribute, we just need to call our object first, because when you want to get an attribute, you always have to call it from the object, and then you add a dot, and there you go, you call for the attribute, and which is here inertia with an underscore at the end. All right, congratulations. I think this was the very first for loop we actually built in this course. So if it is your very first for loop of all time, congratulations. As you see, this is not nasty at all, and you actually built a very useful for loop which will plot very nicely the graph of the elbow method. And now to get out of the for loop, we need to, go back here at the beginning of the row to specify to Python that we are indeed not anymore in the loop and that we are back in the main code. And speaking of the main code, well, the only thing that we're left to do is just to plot the graph. So here we just have to plot the graph. And to do this, well, we're going to use, of course, matplotlib.pyplot, which we will use this way, first by calling the plt shortcut here, and then from which we're going to call the plot function. This is something we already did, of course, when plotting our regression curves or classification curves in part 2 and 3. And now we're about to plot just a simple curve that will follow the different WCSS values taken for the different numbers of clusters from 1 to 10. And so, well, in that plot function, remember what we have to input. First, we have to input the different values that will be taken on the x-axis, and that's the values from 1 to 10. So in order to specify this, well, we can simply take, that range again, because that range from 1 to 10 exactly returns all the values from 1 to 10. So there you go. That's what we can input here for the x coordinates. And now for the y coordinates, according to what are we going to input here? Well, very simply, that's of course all the different values of WCSS. And they have to be input in a list. And well, good news, that's exactly what we have already. And that's of course also the reason why we created that list in the first place, so that we can directly input this into the plot function to indeed plot our elbow method graph. All right, things are starting to get completed here. Now, what else can we do to improve that graph? Well, very simply, we're going to add a nice title with the title function, and we'll actually title our graph by, the elbow method. All right, very simply. Then we'll add a label to the x-axis thanks to the x label function. And on the x-axis, we can specify that it is indeed the number of clusters. Perfect. And now same for the y label, which we will specify to be, of course, the WCSS within cluster sum of squares. And finally, remember the last thing we have to do, which is to show the graph with the show function. All right, so I think we're done here. Let's see if we're right and if we didn't make any mistake. So we're actually going to play that cell and plot the elbow method graph. Congratulations, we did it 100% correctly. So now, according to you, after you followed, the intuition lectures, what is the optimal number of clusters we must choose here? Well, I remind that this is the number of clusters from which, the WCSS value start slowing down, start reducing its descent. And here, well, that's of course that number here, the number 5, because indeed from this number, well, the curve starts being almost flat. It decreases very slowly. Here, it decreases very strongly. It decreases a lot. Here, still quite much. And from the number of clusters 5, well, it decreases slowly. Okay, so clearly the optimal number of clusters here is 5. And therefore, for our next step, training the k-means model on the dataset, we will choose to build it, to train it, and to run it to identify 5 clusters. All right, so let's do this in the next tutorial. And actually, I have an exercise for you based on what we did here to plot that elbow method graph. You can actually totally do this on your own. So actually in the next tutorial, we will train that k-means model on the dataset, to identify 5 clusters. And then we'll also create that dependent variable, which I've told you about. That's the principle of clustering.